Welcome everyone to today's Australasian Fluid Mechanics seminar. Today we've got Professor Tracie Barber from the University of New South Wales speaking to us. Professor Barber's worked across a range of areas in aerospace and biomechanical applications. When I was looking up her biography before, I saw that she's published in an enormous range of journals across a very diverse range of areas, including one called what was it called? Artificial Organs, which I think is my favorite name for a journal that I've come across. So today, Professor Barber is going to be talking to us about optimizing geometry and hemodynamics within an arterio-venous fistula. So thank you very much, Professor Barber.
Thank you.
Oh, sorry to interrupt. Also, Professor Barber is happy to ask any questions throughout her talk. So if you've got a question, you can put it into the chat box or use the raised hand icon at any point throughout the talk.
Although I'm not actually looking at the chat, so someone might have to alert me.
That's okay. Sean and I will.
Yeah, cool. All right, thank you. And thanks very much for organising this. This is a really cool idea to have these presentations done online. And we were just saying before, it's probably something we should have done a long time ago, even before COVID happened. Okay, so what I thought I'd start by doing before I get on to explaining what an arteriovenous fistula is and why we care about the fluid dynamics in it is just to talk in general about fluid dynamics and blood flows. So usually when we're talking about disease in an artery, we're looking at things like the thickening of the vessel wall. And this is caused by something called intimal hyperplasia, which is the first stage of cell damage. And the thickening of the vessel wall is what is associated with things like stenosis, which you might be more familiar with in coronary arteries. And so that's where people need to have a stent put in so that then it widens the vessel. Or sometimes there's ballooning where a small balloon is put in and expanded to expand the vessel. And sometimes if it's very severe, like in the case of my dad, then they need to do a bypass, which is where they actually take another vessel and go around the stenosis to allow the blood flow to keep going. So all of these things are caused by a number of factors, and some of these factors you can see around the chart here. The bottom one, previous vessel wall injury, that could be things like a needle being stuck through the artery. But the other ones you can see are all fluid related. So shear stress, whether it's low, high, or oscillatory, meaning it varies over time. Blood particle stasis, where you've got the blood sitting in one spot. And also turbulent flow, which can happen in certain conditions in certain vessels. Okay. So if we look at, for example, femoral artery, which is quite an interesting case. The femoral artery is a big artery that's in your leg. And you can see that the cycle on this vessel actually goes fast forward and then it has a bit of reverse flow as well. So it's quite an interesting flow profile from a fluids point of view. And if you can see, hopefully these animations, you'll be able to see them. In the top one, what I've done here is just shown where if it's blue, then it means the flow is moving in a positive direction, which is left to right. And if it's black, then it's moving right to left. So you can see that for this, and this is just a very idealized geometry as well, with a stenosis in it that isn't particularly severe. But you can see how much flow variation there is across the geometry. We've got some in the middle going in one direction, some on the outside going in other directions. We've got little pockets where it's moving in different directions across the whole radius. So there is quite a lot of variation. And then in the bottom one here, where I've made this very broad assumption that if we assume the local Reynolds number is below 1500, then it's probably laminar flow. So that means that anywhere it's black could be transitional or turbulent flow. And obviously this is a pretty big assumption, but it gives you an idea of how much turbulence might be generated across the cycle and also spatially across the geometry. So we may have regions where we've got locally turbulent flow that only exist for a small amount of the cycle. So there's quite a lot going on in these flows. Now to just show a bit more detail here, and these ones, we tested these earlier, so hopefully you can see them, but they are on our YouTube site in a bit higher resolution. The top one is an LES simulation of that same geometry, so this idealized stenosis in a femoral artery. And what you're looking at here is isocontours of vorticity, which are coloured by velocity. And so you can see all the detail of the flow features, that there's a lot going on, particularly near the walls. Obviously, in that throat of the stenosis, the narrowing part, we're always getting this high velocity, and that's where we're going to get the high wall shear stress. But in the recirculating regions, where we're getting all the swirling flow, we're going to have flow that's staying in one spot for a while, and we're going to get a lot of low moving flow. You can see this happening at the moment in this region here, where we've got this very slow moving, swirling around flow that's going to be causing a low wall shear stress region. But then you'll see once the jet starts again, once we get to those high velocity regions, that all of this is then swept out. So over the cycle, we get a lot of oscillatory shear stress happening, where it's changing from low wall shear stress to high wall shear stress. And in this bottom image here, so this is again the same geometry, but in this case it's an experimental case, and we've put a laser sheet just right through the middle plane, and we're just highlighting some particles that are in the flow. And in this you can see how much variation there is across the geometry. And in particular, if you look really close near the walls, if you can make that out in the resolution that you're seeing, you can see that sometimes the particles are just kind of sitting there, sometimes they're moving very fast, sometimes they're moving in a complete opposite direction to what's happening on the inside of the flow. And sometimes we're getting a velocity profile that's going to be quite variant across the whole geometry. And this is just an idealized shape as well. So obviously in a real arterial stenosis, it's not going to be this perfect axisymmetric shape. So we're going to expect more disturbances to be generated. So if we go back to that image I just showed before, you can see that all these factors that I mentioned, we're clearly going to be getting a lot of those occurring in a stenosed artery condition. And so the fluid dynamics is going to have a very big effect on whether we're getting that disease initiation. Okay, so on to the arteriovenous fistula, and what is this? So this is a particular surgical creation that happens if you have kidney failure. And your kidneys filter your blood. So if your kidneys no longer work, then you hopefully will get a kidney transplant. Or the other situation is that people need to have their blood filtered externally. And normally this is done via hemodialysis. And this means basically all the blood in your body is taken out and put through a filter, pumped through a filter, and then returned back to your body. And so in order to do this in an efficient way so that you're not hooked up to a dialysis machine 24 hours a day, they need a very fast flow. And so this is normally done in the forearm by taking the radial artery, which you can see here, which is normally the one that delivers a lot of blood flow to the hand. And in most cases, this radial artery is cut here and joined up to the cephalic vein, which you can see down here. So instead of the flow going into the hand, swirling around, slowing down, and then going back into the vein, the arterial flow just turns straight around and goes into the vein. And so it doesn't get a chance to slow down, and it doesn't see this high resistance section of the hand. And what this means is that the normal flow rate that you would expect in these vessels might be 20 to 30 mils a minute. But once you've made the fistula, then you can be getting 600 to 1200 mils a minute, or even up to 2 or 3 litres a minute in some cases, which is obviously a huge dramatic flow. On top of this, we expect this really fast flow to turn a very sharp corner back on itself. So rather than having the slow flow go into the hand, swirl around, and then gently come back, we're getting this fast flow to immediately turn back around. And then we also put a needle into it. So the blood is taken out with 2 needles. The arterial needle takes the blood out, and the venous needle returns the blood. So when the blood is returned, it's coming in as a fairly high-speed jet, which is then impacting on the vessel wall. So not surprisingly, we get a lot of disease initiation around where this joint happens. And the joint is known surgically as an anastomosis. And around the anastomosis, you get these little yellow regions we're showing here, which are typically where we get the stenosis happening. And usually it might start at this size, but because of the very quick flow that we're getting, they grow quite quickly as well until they will block the fistula, and then it's no longer able to be used for dialysis. This obviously is a fairly critical situation, and it means that then the patient has to go into hospital and has dialysis some other way, which is not as effective, and they need the fistula fixed somehow or recreated. And unfortunately, this happens a lot. So fistulas do not survive very well. They do not work terribly well for most of the factors that I've shown you. And so it is a very big cost and inconvenience to dialysis patients, in that they are often continually having surgery to correct these fistulas that are not working. And this is what a real fistula looks like. So this is the artery coming along here, and this is the vein, which you can see has grown significantly because of the extra blood flow going along. And this part down here is the distal artery that goes to the hand. And in this case, we've got an arrow pointing this way, but what we've found is that in many cases, the blood flow is actually coming that way. So it could go either way, to the hand or not to the hand, but there's a very small amount of flow in most cases going to the hand. Most of it is just seeing this low resistance circuit back up into the vein, and all the blood goes up there. Now, the region near the anastomosis, which is known as the juxtaanastomotic region, is where we get most failure happening. And so it's known as juxtaanastomotic stenosis. And it happens in, depending on which paper you look at, 43 to 100% of all fistulas. It's been identified as the major cause of failure to mature. And mature means that after you've created the surgery, you have to wait a little while until you can use the fistula. And some of them just are never able to be used. And it's also the major reason why patients keep having to come back, because there's dysfunction in the fistula and it's no longer working. Even once it's started to work, they continue to block up. So when we first started looking at fistula flows, we thought the place to start was probably looking at the needle flow, because having a big jet of fluid impacting on the wall, we thought was likely to cause a problem, and also likely to cause some downstream turbulence. And you can see this unsteadiness in these images here, and particularly here you can see these vortices that are created. And this causes a lot of flow disturbance to continue downstream, and also obviously we're getting this impacting on the wall, which is causing cell damage in this region. So one of the things we looked at was seeing if we could, what effect it has if you vary different factors that are able to be varied. And so, for example, the typical flow rate is 300 mils a minute for dialysis, but sometimes it might be lower. In some cases, it can be higher. And overseas, we've even seen places where they might run up to 500 or 600 mils a minute. And you can see the effect of increasing this flow rate has quite a significant effect on the wall shear stress along the bottom of the vein. And so this is the impact zone of where that jet is hitting. We also looked at where you could place the needle, whether it's right in the middle of the vein, whether it's right at the top or right at the bottom. And obviously if it's right at the bottom, then that jet is going to be closer and hit the wall more. And so you're going to get more of an effect of the impact. And also the angle, because different nurses will tape the needles down in a certain way, and depending on how you tape it, the angle might vary. Also, if the vessel is is buried quite deep into the arm, then it means that the needle may have to go in at a higher angle just to get to that vessel. And in patients who are particularly overweight, there's also a lot of extra tissue to get through. So some of these factors may not be within the control of the renal nurse. But when we've presented this information to them, they've been very interested, because now they're able to see the effect. Obviously, they're not going to be sitting there with a protractor working out exactly, what degree they're putting the angle in, but they know what effect it will have. They know that, for example, if they have a very deep fistula and they have to put the needle in very deep, then this is something they may need to look at, because it might be causing more damage on the vessel. Now, we then started to look at the actual fistula shape, and to begin with, we made an idealized shape. This one was actually machined out of acrylic in our workshop, and we made a side-to-side one where you can see that both go down, both the vein and the artery go to the hand. By using a fluid that's got sodium iodide in, which matches the refractive index of acrylic, we were able to make this geometry pretty much disappear, which is useful because we do mostly laser measurements, and obviously we don't want to have any of this refraction happening. So then we built a double scale fistula flow rig with double scaled needles, which actually have quite a complex geometry at the tip. We hadn't realized until we asked our workshop to make them. So we built a double scale rig so that we could understand exactly what was happening. This is the rig set up in our lab with some flow visualization laser happening. So we were able to then see what we had imagined was happening and what we'd seen in some of our CFD results, with the flow very sharply going around the corner and not much happening in these distal vessels. We're also able to see what was happening with the needle flow and do some flow visualization and also some planar PIV to just pick up exactly what the velocity was, and also just do a bit of comparison to our CFD and to pick up these swirling regions, which you can see in here. There were some new needles came out as well that are plastic, and they're not used much in Australia, but there's quite a lot of interest in them, and they're used almost exclusively in Japan. So we were asked by the company that makes them to have a look at the effect of the plastic needle versus the traditional metal one. And it was quite interesting when we studied this, mostly because it's got this tapered section here, and also it's got these side holes. And so what we found was that this is the metal one here and this is the plastic one. The biggest, the main advantage we found in the plastic one was that the tapering in the side holes meant that the jet was dissipated quite a bit earlier. And so we didn't have as much effect of the impact on this lower wall. And also the disturbance didn't continue as far downstream. So going back to the fistula shape, I mean, clearly you can see from a fluid's point of view that if you've got this flow going very fast here and then turning a sharp angle, then it's not going to be ideal and it's going to create quite a bit of disturbed flow. So we started having a look, just from a very theoretical point of view, what would be a better shape that we could make. And we started with a 2D analysis, and we looked at just optimizing from a two-dimensional shape what would be a better shape and what would create a smoother flow through this geometry. Once we'd made some better two-dimensional cases, we then ran these in 3 dimensions and came up with some much smoother geometries. Now, obviously, there's not much point in creating things like this and doing it all in CFD if it's not going to actually be feasible. So along the way, we worked with a couple of vascular surgeons who actually make these fistulas, just to see what would actually be possible. And we started saying, you know, could you actually make a vessel like this and curve it around? And they said that they could, and they had made some like that for some reasons. And that if there was, you know, there seemed to be an advantage, then that was something that they would look at. So we looked into more how could we change the vessel and what the actual effect was. And so this is the typical shape here. And you can see this, basically the flow is coming along here and whacking into the wall and then gets pushed against the side here. And you end up with a very disturbed flow in this region. And you also end up with quite a lot of disturbance in the distal part. In our nice smooth loop version, we've got the flow coming around and it's not hitting the wall so much. We still get a little bit of disturbance here, but it's a much smoother flow. And so then we're getting a lot less disturbance. But as I mentioned, this is what a real fistula looks like. And it's not a beautiful smooth curve. It's not a nice round diameter. There's little vessels coming off everywhere. The shape is not, you know, nice and uniform. And also there's a lot of variation between patients. They certainly don't all look like this at all. Every patient looks very, very different. So we realized that if we were going to do anything that was really helpful, then we needed to stop looking at the idealized models and actually try and get some patient data. The problem with this is, though, that kidney failure patients are unable to filter out any sort of dye. So it's very uncommon for them to have any sort of imaging technique where a dye might be passed through, unless they're actually having surgery or something like that. So for us to just say we wanted to get the geometry from all the patients that came through the clinic of the surgeons we worked through, that was just not going to happen. So we had to develop a non-invasive technique. And so what we use, this is us set up in the Prince of Wales Hospital, where under normal circumstances we go up there every week, but obviously at the moment we're not up at the hospital. But the last couple of years we've been going up there every Wednesday afternoon, where one of the surgeons holds a vascular access clinic. And so what we have is an ultrasound machine here, and at the top here is a 3-camera infrared system. And this is Eamon, one of our previous PhD students, and he is scanning. This is actually not one of the patients. This is Sanjeev, one of our other PhD students pretending to be a patient. And so we actually scan the patients, and on the probe we have these little tracking balls, and the tracking balls are then monitored by this camera. And over here is John, one of the other guys, who is running the MATLAB code, which you can see in the background here, is getting all those images off the ultrasound machine and joining them together. This is John and Eamon putting together one of our earlier versions, and here we were just demonstrating how quickly we could set it up. You can see it's an earlier version because we've got this ugly tripod on the top, and also there's a horrid mess of cables here. It looks much better now. But we actually bring the system up from the university every week. So this was just a sort of demonstration of how quick it actually is to set up. So the way this works is that we get all these slices. These are the individual slices. And then using, you can see these tracking balls here. So the camera works out in 3-dimensional space where the probe is as you scan down on the patient. It then is able to put them all together into this volume, which is here, the stack of all these slices. And then from these slices, once we've got them together, we can extract out this geometry. And so this gives us a very accurate representation of what the geometry actually looks like by doing it completely non-invasively using ultrasound. Yeah, the next photo has got a bit of ugly surgery, so if you don't like this sort of thing, you might want to look away. So because it is a very non-invasive and very easy to set up technique, it meant that we were able to take it into the recovery room. So we were able to scan patients immediately after they'd had surgery. And so, for example, this is John, one of the postgrad students, actually in the theatre with, this is Shannon here, who's doing the fistula surgery. And we were, in the initial stages, we did just a sort of qualitative check. So this is the scan of the fistula. And we're able to just compare visually and say, yeah, it actually looks exactly what we think it looks. So for this patient, for some of the patients, we're able to scan them before they had the fistula created. So the blue and the green are the artery and the vein before the fistula, and then the red is the post-scan. So immediately post-surgery in the recovery room, we're able to scan the patients and get the geometry. As well as scanning the geometry, we also get Doppler profiles with our ultrasound machine at each of the 3 vessels. I'll just pause these. So we do a Doppler here, here, and here. And the green line is an ECG that we also use on the patient at the same time, which gives us kind of a baseline of these peaks so that we can sync up the 3 flows. Because sometimes the peaks, this one isn't too bad, but sometimes, particularly in the vein, it can be very turbulent and it's not obvious where the peaks are. So we use the ECG as a way of being able to segment into those cycles and sync up the 3 different boundary conditions. So we now have a completely patient-specific geometry and patient-specific boundary conditions for each of these patients, which means we're then able to run very detailed CFD. And this is a case where we actually had one patient who we followed for 15 weeks. And every week we saw him before he had the surgery, and then every week he came in and we scanned him. So we were able to track how his fistula was growing and maturing over the 15 weeks. This is showing the shear stress. And one of the interesting things we found with this was that people had assumed that it would go back to a baseline shear stress, and the fistula was growing and changing to try and get back to this baseline. And what we found was that, yes, it was going back to a baseline, but it was an elevated baseline from what it was before. We were also able to track how the fistula grew. And interestingly, we showed that the vein, the change in the size of it was almost instant, but the artery took quite a long time, and it was continually growing over time. Now, with some of the patients, some of them we only see maybe once or twice, and some of them we see quite a few times. And so we're able to track the progress of their fistula. So for example, this patient we saw, and they had 2 stenoses forming here. Shannon, the surgeon, put a stent in. Not long after, we saw the patient again, and another stenosis had occurred here, which is quite common. Shannon then put another stent in to correct the stenosis, and it went around the juxtaanastomotic region and also helped to create this shape that we'd been talking about that we knew was favorable. And you can see in the CFD, you can see in the flow rates here that the flow rates have increased dramatically. But also in the flow, you can see it's a much nicer, smoother flow. And we're getting that geometry that is pretty close to that idealized one that we showed. We started to come up with a way that we could quantitatively assess different fistulas. And the one that seems to work the best is based on a type of resistance. So using our CFD results, we calculate a resistance for both the arterial section and the venous section based on a pressure difference and a flow rate. And so, for example, taking this patient here, you can see we saw them twice, and in this time, the stenosis got much worse. And you can see the flow rates here have dropped, and you can see from the CFD this pretty horrific flow and how much worse it's got once there is a stenosis. Now, if we calculate resistance for this patient, so the red part is the arterial resistance, and the blue part is the venous resistance. If I just go back to this image, this is the vein at the top, and this is the artery at the bottom. So you see there isn't a lot of change in the artery, but the vein is having this big change. And that's where we see this big jump in the resistance, and it's caused by that venous stenosis. This is a patient we saw a number of times, and you can see that this patient had a juxta stent put in this region here to correct the stenosis that was just near the juxtaanastomotic region. You can see how it looked at S3, the third scan, where there's a pretty bad stenosis. And then we get this really nice flow with the smooth loop shape in S5. So looking at the resistance, you can see the S3 with the stenosis is huge with this big venous part, and then drops right down once we get the nice shape put in there. Another example, this was the one that I showed just before, where we had the 2 stenoses, another one occur, and then the juxta stent with this really nice looking flow. And again, big drop once the juxta stent's put in. So what we're doing now is combining all of our patient scans into one big database. And we're hoping that if we can get enough data on all these patients, then we'll be able to come up with some sort of predictive tool. So we'll be able to say, if your resistance is this value, then this is bad, or if your resistance is this value, then you're safe. What's becoming, I think, clear is that it may not be one scan that's enough. Often what we need to do is have a look where a patient is moving. So for example, this one, these two were fairly close together, but if we'd seen that, I mean, they're already in a fairly high region anyway. But if they'd started here and they'd moved up to here, then if they've moved up a fair bit and there's a bit of a gradient happening, then I think this is going to be a warning zone even before we can actually see anything on the ultrasound scans. So this is the one that I showed just before, when you can see that the two with the stenoses are in this sort of mid-range here, and once it's fixed, it's down in the smaller region. What we can also see from these is just by looking at the division of the blue and the red, so how it divides up between the arterial and the venous, we can work out where the problem is. So for example, these ones here, you can see there's a big section that's blue that is causing the resistance. So these are ones that are going to have a lot of venous resistance. You can see there's one just here, which has got only a small amount of venous resistance. And the red part here is from the arterial resistance. And this one here was caused by there being a very small arterial artery inflow. And so we can actually work out not only if there is a problem, but what the problem might be just by looking at what the resistance is and the breakdown of that resistance. But we can also, you know, I was saying that we probably need a gradient, but some of the cases, you know, this is a pretty horrific looking fistula. It's got this really acute angle. It's got a stenosis here. It's really curvy. And it turns out to be one of the ones up here. This one, really nice big fistula, reasonable radial artery inflow, really nice smooth loop curve here, and it's one of the ones down here. So even with one number, we can still get a bit of an idea what's happening. So at the moment, we've been stopped a bit because of COVID and that we're not getting any more data at the moment. But at the moment, our work is trying to develop this predictive model. And Olivia, one of our PhD students, is going through all the patient records to try and correlate exactly what we're seeing. You know, we look at these resistance values and we say, okay, what we think happened here was maybe they had a stent to correct something. And then we're going back and checking to see if that actually happened, if we don't already know, with the patient. We also 3D print a lot of fistulas. Originally, we started doing this just because we had 3D printers and, you know, why not? And it was quite interesting to see them. We'd been used to seeing them on screen and they were like big, and then we realized they're actually really tiny. And, you know, some of them are only a few millimeters in diameter. So we suddenly had an awful lot more respect for the renal nurses being able to put those needles in there. But it was also, this is a shelf in the lab where we have a lot of 3D prints. It was also useful to just see the variation in fistulas. This one at the top was one where it's the same patient been scanned twice, and they they had a bit of an aneurysm here, and here, and then a stent was put in which corrected it. But you can see we've got another little bump happening here. These really large ones here tend to be brachio ones, which are in the upper arm, and they tend to just grow larger. But you can see there's a lot of variation, some very little ones, you know, some very bumpy ones. So it was quite useful for us to see these and to use as education for both the renal nurses, and also we've given quite a few of these to patients who wanted their own 3D print of their fistula. But being able to 3D print them then opened up some other avenues for making our experimental models. So what we do now is we 3D print the fistulas. This is the plaster one. We've also done them in wax and PVA and PVB, and we're looking at a number of different materials. What we then do is we make, in this case, a very over-engineered box, and we pour in PDMS, which is a type of silicon, and then we dissolve out the 3D print. And so we're left with this really nice, pretty accurate patient-specific geometry, which is optically clear. And because it's silicon, we don't need to use sodium iodide, which is pretty horrible to work with. We just need to use just sodium chloride and some glycerol, and then we can make these ones disappear. So this is the lab at the moment. Actually, this afternoon, I realized I didn't have a particularly good photo, so I went in and took one. And these are some pulsatile flow pumps that we've built in-house. We also have a commercial one that's hidden behind the sides here. We have, this is the PIV system, which I think I've got another photo of. Yeah, so this is, at the moment, that's just a calibration plate set up here, but normally this is where we have the fistula model like I've just shown you, we've got one that we're looking at in a lot of detail that is normally sitting here, that at the moment we're doing tomographic PIV to try and get some more information about what the flow is doing. These are some of our initial stereo PIV results, which gave us some really good information that correlated well with the CFD on exactly what was happening in the flow. And recently, Sanjeev, one of our PhD students, has been working on getting the tomographic results. And these are some of his quite recent results showing the velocity contours going through this fistula, which is showing the exact sort of flow features that we've been seeing in the CFD. And also just giving us some more interesting detail about what's happening in these regions. Let's go to the next one. And this is also showing, this is isocontours of turbulent kinetic energy over the cycle. And sorry, I should point out that this is the cycle down here. And so you can see that we are seeing, you know, evidence of turbulence being generated during the cycle and varying quite a lot spatially as well. So one of the things we're really interested in seeing, because this is the geometry that has been created by a stent being put into it. Our model does not have the stent, and it is just the overall lumen shape, so the blood flow. But what we'd really like to see is the effect of the stent struts on the turbulent generation, because obviously that stent is lying right against the wall inside the boundary layer. And so it may be affecting how this turbulence is being generated. But stents are made of metal, and so it's quite difficult. We have seen other people have done PIV around a metal stent. We're yet to try it. We've tried 3D printing a stent, but they're just too little. It doesn't really work. But what we're doing instead, so this is an angiogram image of the stent inside a fistula. And just a bit on the stent, it's a particular type of stent. A typical one looks like this, and so it's made of usually wire cut, and it's, you know, it's a bit kind of like chicken wire, but obviously much smaller and probably made of more expensive material. But if you bend it, then it crumples and it squashes. The type of stent that we're using, well, when I say we, obviously the surgeons are using, is known as the superior stent, and it's made by Abbott. And it's actually for use in the popliteal artery, which is an artery that goes around your knee, so that when you bend your knee, it doesn't crack like this. And it's an interwoven stent. So instead of being wire cut, these wires are actually interwoven. And that's how it's made. So it's kind of like a slinky, and you can move it around and it doesn't swash. And it also compresses very well as well. So that's how it can be made to go around the corner of this fistula. So what we're doing now is making PDMS models of all our juxta-stented fistulas that we've scanned. And you can see some of them here. I think these might be PVB prints. And then once we've dissolved this out, we take them up to Shannon, the surgeon, and he looks up the exact size of the stent that he used in the patient, and he deploys the stent into our models, which he says is actually harder to do than in the patient, because the PDMS is, it kind of doesn't slide as well as inside a vessel, which was interesting. This is what it looks like if you put it into some glycerol. And so you can see the stent being deployed in there. And usually Shannon checks against an angiogram so that we can see that it's been deployed in as much as possible the same way that it was done in the patient. This is a close-up of the stent where you can see this kind of interwoven geometry and how it does go around the bend very nicely. So we've been doing a number of these scans. You can see they've all got these really nice curvature from putting the stent in there. And getting the stents deployed into these models. Now what we're doing is eventually we want to try doing some PIV directly on these, but like I said, it is metal. We are asking Abbott, because we're working a bit with Abbott now, and we're asking them if there's any way that they could possibly make one that's black, so that it won't reflect the laser. But in the meantime, what we're doing is we take these models that we've made up to our biological imaging lab at the university, and we do a micro CT scan. As I mentioned, it's not really possible to do this on a fistula patient because it's just not really ethical for us to do this kind of imaging on patients who you know, don't have a way to get rid of the dye. So they only do any of the kind of imaging unless it's a real emergency situation. So what we're doing is what we figure is the next best thing. So we've got this geometry that we believe is really close. The PDMS is firmer than it would be in a blood vessel, but Shannon thinks that the end result is very close to what he gets. And so we have this stent deployed. We then do the micro CT scan and we get a huge level of detail that we can then recreate. So what we're now doing with this geometry is we're running CFD simulations. And at the moment, we're just making the meshes of these because obviously it's a fairly complicated geometry to get an accurate mesh on. But that's the stage we're at the moment. So we're hoping that with a very good CFD model, even if we can't get the PIV to work very well around the stent, that we'll be able to understand what is happening with the flow field around those stent struts by the CFD. And this should be a pretty accurate representation of the geometry that's in the patient. And just some patient data. These are some various interventions that have been done in the juxta region, and the bottom one here is I think they're up to about 60 patients at the moment. When this study was published, Shannon had 42. And so they're getting really good results, very good patency. There's different ways of talking about the patency, primary, assisted, and secondary, which basically is to do with how long the intervention lasts before you need another intervention. Secondary means that you had to abandon the vascular access altogether and make another one, or fix it, you know, in some completely different way. And you can see that the secondary patency is 100%. Also, what's really important is that there haven't been any fistula losses in the study. And Shannon has mentioned that in the fistula clinic, he thinks that it has become quiet since the superior stents have been starting to put into the fistulas, because a lot of the patients are just not coming back in the way that they used to do. Okay, and so just finally, the people who've been involved in the study. So these are some of the people who've worked on the project at UNSW. At Prince of Wales, Shannon and Ramon are the two vascular surgeons we've worked with there for a few years now, who obviously have a great deal of input into the project. And we come up with these fabulous ideas and they tell us whether or not they're actually feasible. Sue and Debbie are two of the renal nurses who have also helped us a great deal in working on this project and have let us near their patients as well. Renal nurses are particularly protective of their patients, I think, because they see them a few times a week. And they have both been amazing and letting a bunch of engineers into their clinic. And Abbott Vascular, who we now work with a bit because they like what we're doing with their stents, and they've been giving us a lot of information. And Andrew Neely told me I had to have a picture of one of my dogs, so this is Torch. And happy to answer any questions.
Thank you, Professor Barber. That was a really great talk. I especially enjoyed your 3D printed veins and arteries. They reminded me of ant tunnels underground.
Yeah.
You had a question, did you, Sean, or is that just a clapping icon?
It's just a clapping icon. I'm happy to give the floor to people.
So we'll throw the floor open for questions. So while people are just collecting their thoughts, I just wanted to ask you about that longitudinal study, that 15-week study slide you showed.
Yeah.
It looked like in the sort of maybe what would be the regions of laminar flow that there were kind of standing waves. I'm wondering, is that an artifact of the imaging or are they actual standing waves due to the heartbeat? Laminar regime?
Was that the shear stress one or?
It was where you had 8 different images.
Yeah, let me just see if I can go back to that. This one, I think.
Yeah, so if you go, yeah, sorry, that one you just had.
There.
Yep. So,
Yeah.
I mean, they look like really nice standing waves. I mean, is that really what happens in an artery or a vein?
No, that is actually, like you say, it's part of the imaging.
Okay.
And
Gotcha.
we do, yeah, we have, and it's interesting that we've been looking at this particularly with the stent recreation from the micro CT at the moment, in that when we segment a geometry, we do it in slices. And so you do end up with this kind of waviness, which is, you know, what you've pointed out here.
Yeah.
And it's how much do we smooth it and how much do we keep that kind of roughness to get a bit of realism in there. And so we've been looking at that a lot with the stent recreation. And we actually went back to Abbott and said, you know, what is the surface roughness of the stent strut so that we can segment it to an appropriate level. But yeah, it is, I mean, it is a problem because we are joining together all these slices, and we do use a lot of slices, so we do get a lot of spatial resolution, but we do end up with, yeah, as you pointed out, a little bit of bumpiness there, and it's always a bit, how much do we, you know, smooth that out, and then are we actually losing some of the critical geometry?
Yeah, gotcha. And are you confident that when you do these CFD models of the stents that you will actually have sufficient resolution to do that? Because it's a very finely detailed structure you're trying to model there.
We think so. At the moment, we're still trying to get a really good mesh around the stent struts. And I mean, it's going to be an enormous mesh once we do get it made. And even when we look, I mean, the stent strut should be perfectly circular because it's made from wire. In our segmentations, they're not perfectly round. So we know that it hasn't been made completely correctly. And, you know, I mean, we could go back and try and turn them all into round. But, you know, one of the things we've been looking at is how many points do we get around the strut? Because, you know, obviously if you only put like 10 points around, then you're not getting a circle at all. So it is, yeah, it's a very difficult one to do. And we've done, we have done some stents in bifurcations, peripheral bifurcations before, and run meshing on that. And it is possible to get reasonable results. And because we want to look at the turbulence generation, so we want to look at another level of resolution than the studies that we've done before. So it's, yeah, it's going to be tricky, definitely.
Yeah, I'm sure.
Yeah.
Anyone else have any questions for Professor Barber?
I have some questions while other people are gathering their thoughts, if that's okay, Dave. That was a really interesting talk. Thank you very much. One of the questions I had was for the Tomo PIV of the like, how do you even do that? Like, how do you get the laser sheets when you have, I guess is it acrylic that's the surrounding and the blood vessels are empty?
Yeah, so we've got, these are now the PDMS models that we make with the patient, because this is a patient-specific one we're doing now. So that's how we 3D print it and then dissolve it out. We've definitely had, we've got 4 cameras, and we've had the cameras in, I don't know how many different configurations to try and get the best, you know, the best position for them. At the moment, it seems to be pretty good. We had a number of issues, you know, at the start, just getting the resolution and getting, you know, just being able to see all the right particles. But I think at the moment, when we're only capturing a very small section and that anastomosis as well, and we're not going the full width of the fistula. But it's, I think, I'm just trying to think how long, I think it's been 2 years we've been setting that up, and those results are probably a few weeks old.
Okay.
So it's been, and that's been the process of not only just setting it up for that, but also working out how to get a really good model, how to get it, you know, clear enough. Also how to get the waveform, because we want to try and get a very accurate patient-specific waveform, but we've got 2 inlets. And so rather than using 2 pumps, we've just been trying to connect up the pump in a certain way so that we can get very close to the patient-specific profile. Because one of the things we've found is that a lot of earlier work was done using either idealized geometries like we did, or else they might have gained the patient geometries in some way, but then they assumed what the flow conditions were. And what we found is that it's really critical to use the right flow conditions. Otherwise, you may as well be modeling any sort of geometry.
Just in terms of doing the calibration for the Tomo PIV, where is the calibration plate placed? I imagine also it's hard to get the right illumination within the blood vessels and on the calibration plate simultaneously.
Yeah.
I'm just wondering, like,
And
logistically, how is that achieved? That seems quite incredible that it's possible.
so what we do is we've got a calibration plate, and we have basically encased the calibration plate with a block of PDMS, so that it's, I mean, ideally we would like to have the calibration plate, you know, if we were doing a wind tunnel, then we would just have the calibration plate in the wind tunnel and you'd go through the wall and you'd do it like that. But with our model being the size it is, then there's no way we can do that. So, and we do the same with our LDA system. We build whatever thickness of PDMS or acrylic that we need in front of the calibration, and then we calibrate it, and then we put the model back into the same position.
Okay, that makes sense.
But it's certainly a bit harder, and there's definitely, you know, error involved in not having the exact same model there. And we see this a lot with the LDA, because you get it perfectly aligned and then you put the real model in and it's no longer perfectly aligned. So.
Right, thank you.
Gary Rosengarten had a question. Would you like to unmute and go ahead, Gary?
Yeah, I've even put my video on because I haven't seen
Hey,
Tracie
Gary.
for a while. Hi, Tracie. And I see you've got the Grim Reaper in the background behind you.
That's my daughter, Ivy. She's got a hood on.
Oh, right. Just a question clinically. So the way I understood it, you take your little scan and then to get all that pressure drop data you had with the multiple patients, and you see the higher pressure drop means is it a problem that you want to do something about, right? Is that, could you, I mean, you have to get the geometry and then import into CFD and then run the CFD. So I guess that's quite time consuming and expensive. Could you just look at, let's say, an average area? Because I assume most of it is area based. Have you looked at that?
And that's a really good question, because one of the things that we've found is that we have this system that seems to be working really well and gets really good results, but it needs, you know, a $50,000 ultrasound machine and 2 PhD students and a professor to run it. So it's not going to be used in every dialysis clinic any day soon. One of the things we're trying to do is come up with either a cheaper system, and we've applied for a couple of grants where we want to try and actually build a system that will do this without needing all of us, but also try and, like you mentioned, try and come up with some kind of correlation. It's very hard to measure pressure without doing it invasively, which is not an option for these patients. But we are looking at different methods. There aren't any, we've tried looking at just things that are measured with ultrasound, for example, resistance index and pulsatility index, which are used, they're often used a lot in fetal medicine actually, and we've tried using things like that, but it doesn't seem to correlate. One of the things we're looking at the moment is just to see if there's a way we can do like a 1D model and see if there's a way we can correlate with that. We're hoping that once we've got all this data, then we can use that as a basis to try and work out if any of these simplified models are something that we could then pass on so that it can be used in other clinics. Because it's a really good question, and that, you know, it seems to be working really well, but it's only working really well at the Prince of Wales Hospital because that's where we are and we can't easily move it to other places. You're muted, Gary.
I think you're muted.
Sorry. It's not dissimilar to the problem we're working on in sleep apnea. We've got pressure drop, which is driving treatment response, and it's the upper airway. So it's quite, maybe we'll have a chat later.
Yeah, it's definitely very similar. I guess the only difference is at least it's slightly easier to measure the properties. But yeah, it's a very similar problem in terms of, you know, we come up with these great engineering solutions, but to make it clinically useful is a bit harder.
Anyway, that was a great talk. Thanks.
Thanks. Nice to see you.
Likewise.
Do we have any other questions for Tracie? Okay, well, then thank you very much again, Professor Barber. That was a very interesting talk.
Thank you.
And yeah, thank you everyone for attending today.
Thank you.
Thank you very much, Tracie.
See you, everybody.